Good morning. This is AE483 Automatic Control Systems 2. I made a brief introduction last week. I had a small presentation for those who weren't there. You didn't miss anything. The idea here is to have a quick go through the syllabus if you haven't been here last week, and then we'll start the course. Basically, this is a modern controls class. It's an undergraduate class. It's an undergraduate level, right? So therefore, I'm trying to be as simple as possible in the course. However, we might get things might get a little bit complicated, a little bit more complicated than a typical undergraduate course, okay? So modern control is basically mostly focusing on state feedback control. I will tell you what that all means. It also has a lot to do with optimal control. There's some sort of an optimization in the controller. And we will talk about concepts like observability, controllability, Lyapunov stability, and things like this, which are a little bit beyond classic modern feedback control. So I told you before that this course really doesn't have a textbook. I have a bunch of references. The syllabus will be on the website, so don't worry. No textbook, but a bunch of references because, as I said, this is an undergraduate course that I'm kind of put together, that I did kind of put together in order to make it a more course that is understandable at the undergraduate level, let me put it that way. So if you look at course topics, the first one is Introduction and Review. We will have a review on linear algebra. Linear algebra is of course a very large field of study, so it's impossible to review everything in a few hours, but I will just put down the essentials and things that we might be using in this class, right? So in the next few hours it's going to be a review basically on linear algebra. There we will look at eigenvalues, eigenvectors. I'm sure you have seen this before, but you will hear it from me again. Then we'll look at decomposition, canonical forms, and things like that. After that, finally, we'll start state feedback controller and observer design. The second chapter is basically classic state feedback control. When I say classic state feedback control, science it sounds a bit funny because when we say classic control, we usually mean the single input, single output systems. So, and then we'll talk about the linear quadratic regulator, the optimal control problem. We'll look at the Riccati equation, the LQR controller, and finally we are going to go a little bit into nonlinear systems just so you understand what real life looks like. And there we're going to look at Lyapunov stability analysis. So this is kind of the syllabus. As I said, it will be on the website. So I would like to close this and start immediately with the first chapter here. So this is a document that will be on the website. Okay, so you can take notes, of course, but you don't have to write everything down. I'll put it on the website. This is basically things in linear algebra that I think are essential for this class, basically. Okay, review of linear algebra essentials. That's why I call it essentials, because it's essential for this class to understand these things. All right. Okay. Why am I doing this? The reason we do this is because, let me just do this 1 second. Okay, the reason we are doing this is most of this class will be in state feedback control. So when I say state feedback control, I mean a system with a state X that kind of looks like this, where X is the state and U is the control. Okay, so that's what we're looking at. X is the state, U is the control, so this is a dynamic system. It's obviously a linear system. A and B are matrices. They are matrices, okay? So, and the output here might be Cx plus du. Well, if you look at the system, it will actually look like that. The input will be U, right? And the output is y, all right? So the system looks like this: x dot equals ax plus bu, and y is equal to cx plus du. Now this is a linear system, and x is a state, and these are both vectors here. These are all vectors. Let me put it here. Y is the output, and yeah, that's it. So y is the output. So all of this, x, u, and y, are vectors. Okay? So when I say I design a feedback controller, I say I feedback this, and here I have a controller. Let's not say k actually, let's say controller. Controller, edit as a feedback, and let's say the command being R here. So the controller is actually feeding back a vector. Okay, it is feeding back a vector. This is a little bit different from your classic control, where you had an input U, and then you had a transfer function, say, okay, and then you had an output Y, and then you had this, and then you had maybe multiplication with a k plus minus. Here what we're looking at is, this is a scalar. Okay, it's not a vector, this is a scalar. We call this a single input, single output system. Output system. And often this is, therefore, so single input, single output system. Okay? So this is a scalar, this is a scalar, therefore this is a scalar, these are just numbers. They are now vectors here. Okay? And here you might have only one dynamic equation, a one-dimensional differential equation, or we just write it as a transfer function very often, right? You write it as a transfer function. So it's a single input, single output system. So this is what we had in classic control. This is where we plot root locuses, look at Bode plots and things like that, right? Now the difference between this and this is that we are actually feeding back a vector. We are feeding back the whole vector, okay? And for a majority of this course, we will assume that the output is actually the state itself. That's why it's called state feedback control. We are feeding back the state, not the output. If I feed back the output, we would call it an output feedback control, okay? But this course specifically concentrates on the fact that the output is equal to the state. In other words, here in this equation here, these matrices, y is, for the majority of this course, not always, but for the majority, is equal to identity matrix instead of C times X, and D being 0, so therefore Y is equal to X. So C is equal to I, identity, D is equal to 0, and therefore Y is equal to X. Then the output becomes the state vector itself, so we feed back the state vector. And this is what we call state feedback control, okay? Feedback control. Because we are feeding back the state. If you want to be really precise, you might want to say full state feedback control, because you're feeding back the whole state into your controller. Now, Now, because this is a vector, if you had a k matrix over here, like this, like a feedback gain k, it will not be a number, but it will be a matrix, right? So it will be a vector times a matrix. The output will be another vector, and it will get back here, and this u could be multiple, could also be a vector, and therefore this could be a vector, this can be a vector, and this can be a vector. You have matrices and vectors, and you will have most of the time a matrix over here as well, instead of having k. So a typical state feedback controller would look like this. Remove this one, and you would have a k matrix instead of a scalar. Here this is a scalar number. Here this is a matrix. Okay? State vector, matrix, and all that. So this is what we are looking at in this course. Okay? This is what we are looking at. Now, why is this better, you would think, or you think maybe this is better. Why do you think one or the other is better? If you were in my presentation last week, I told you that this work, if you optimize this k with an optimal k matrix, is really something that's been done after the 70s, after the 1970s. This was worked very intensively. Okay? So this is a little bit older. And you see it's a bit simpler too. You have scalars and things like this. Why would you think that this is a bit better? Or do you think it is better? Well, I guess it must be quite obvious. You're feeding back a lot more information, right, than this one. Here you're feeding back only a scalar. Here you're feeding a lot of information. So how would this translate to real life? Okay? In real life, what happens is, let's say you have an airplane, okay? And let's say you have controls on the airplane, say an aileron. Let's say you have an elevator here. And let's say you have a rudder, okay? And let's even say you have some sort of thrust, okay? So the output here, I'm sorry, the actuation here, the input to the system, U, are really these control surfaces, right? U would be, for instance, it would be a vector. It would look like this. It would be the aileron right here, the movement of the aileron, maybe the angle of the aileron. It would be the rudder, right? The angle of the rudder here. It would be the aileron here, the movement of the aileron, maybe the angle of the aileron, and it might be the thrust vector or the position of the throttle, let's say. Okay? So this would be the input. This would be the input to the system. So this would be actually this here, the input to the system. So you give it as an input to your system, and the system will do something. Let's say you change the aileron setting and you will roll, right? So it will give a response to your input. Okay. So what will be the response? What will it do? Well, that's the output. Okay, that is the output. Well, that's what comes out. You give an aileron input, the aircraft will start rolling. So you will have a P, right? A roll rate P, and then you will produce a phi, and maybe because of the dynamics, you might even get some pitch, or you might just be falling down. You might get a side slip. You might get a side velocity, and things like that, right? So that would be the output. Okay? What happens in time after that input? That is all your output. So how do we do this in real life on an airplane? We take the output, multiply it with a number, and add it here. How would you do this in real life? Well, we know the airplane has a phi angle, the airplane has a roll or a pitch, whatever. How do we measure all this? The way we measure this is actually we have a lot of measurement devices on the airplane, right? Lots of measurement devices. For instance, we have a gyroscope. Okay, We have a gyroscope. What does a gyroscope measure? It measures angular rates, right? It gives you P, Q, and R. Okay? And if you initialize everything right with a set of accelerometers, right, you could even estimate theta and phi. With accelerometers, obviously you measure acceleration in each direction, but if you take an integral appropriately, let's say, you could also measure velocities, accelerations. So you would get UVW. The three velocities in the body axis system, the three velocities, you will get UV and W. So you measure all this. So what are these things? If you're taking flight mechanics with me last year, which is, by the way, also on the web, if you haven't taken that class, you can go back and you look it up in YouTube. All these variables are the variables that are used to describe the motion of the airplane, which we call the states of the airplane, right? We have established that we need really 8 variables, 8 states to describe the rigid body motion of the airplane in space. Okay? So here I have 8 of them. So this would be these would be the states for a typical airplane, the rigid body states during its flight. So you give me these 6 variables, I can kind of tell you what the airplane is doing in space. Okay? So these are the states. So if the states, where are the states here? They are here. X is the state. Okay? So if x is equal to the output, what I'm feeding back in the state vector are all these numbers. P, Q, R, theta, phi, U, V, W, all these states can be fed back. Okay? You're feeding back all these numbers. And they will be multiplied with something. And the output should be another vector. You subtract it from the pilot input, and it should give me the actuator positions. Okay? So how is this possible? How do we do this in real life? Here is how it happens. Well, the pilot is sitting here, of course. Okay, I'm going to exaggerate this a little bit. With a pilot stick, right? And the pilot stick is connected to these controls, right? So when the pilot moves the pilot controls, these control surfaces will start moving. So this is basically, the pilot is here. The pilot is moving those control surfaces, and we see an output. So this is the basic airplane. So this here represents the aircraft. Okay, this represents the aircraft. So the pilot gives an input to the surfaces, and the airplane does something, and the result we read through the states. So inputs and states. Okay? Good. Well, somewhere in between we need to intervene with the pilot. We need to change the pilot input somewhere and do something over here. So the way we do it is the following. We have all these measurements. Let's say the blue box is the measurement. So we take P, Q, R, theta, phi, psi, and all this. And we add a little computer on it, or a little microcontroller, or something, something that can make a calculation. Multiply this measurement that is in this blue box with this little red box. We multiply it, right? We multiply the state with a matrix K. Something that can multiply a matrix and a vector is good for us. So we measure everything through the accelerometers, gyros, sometimes a GPS, a compass, etc. The more you have, the more accurate you are. That's a whole different world how you measure things, right, on an airplane. How you filter it, how you fusion all the data. This is all a different world. But let's say you did this. What happens then is you take this control, the measurement, multiply it with a vector k, and now you need to add it to the input. So at this point, what you do is we move the pilot from here to here. The pilot will do this. So the pilot has moved now here. So the pilot is no more connected directly to the aircraft. He's taking a step back, and we will change his input and send to the actuators the changed input. Okay? We are not sending the input as it is, because when the pilot was here, it was directly connected to the control surfaces. Now, he's no more connected to the control surfaces. He's here. The pilot stick, the pilot control is now R. So we will intervene, change his control, change his input, and send that to the aircraft. So we are in the middle. The pilot will give an input. Let's say he wants to pitch up. So it does this, expects the airplane to pitch up. But we will alter or change the control input that will go to the actual elevator. So there's no more one-to-one connection between the pilot and the controls. We intervene with his controls. How are we doing this? Well, we do it like this. So we cut this line. We say, pilot, this is R now, your pilot stick position. We take this position. We put another actuator over here. Actuator meaning a servo, a hydraulic, something like that. Connect that control system to that servo or to that actuator and send that to the controls. Okay? So what goes out from this box is U. Okay? Now that actually goes to the control surfaces. Okay? The pilot here, this one here, this is R. And this is U. Here is where we multiply everything with K, and here is the measurement X. And this is U. And this is typically what happens in airplanes. So how does it work? It takes R from the pilot, adds or subtracts a number from these inputs. We do it here through this actuator. And that goes into the control surfaces of the aircraft. And the output will basically be a state vector. And the state vector will be measured, again, by the measurement devices. Again, multiplied with K. Again, change this, do that. And how many times would you do this? Typically, we do this more than 50 times a second. This loop circulates 50 times a second. If it's a fast airplane, it could be about 100 times a second. You call it 100 hertz. Right? 60 hertz would be 60 times doing this in a second. So 60 times a second. We would look, we would measure, multiply with a K vector or a matrix or a controller, whatever, subtract it from the pilot controls, and whatever the pilot input here is, it will go to the control surfaces. And then we look what happened to the airplane. Multiply it again, send it back, do this 50 times, 60 times, 70 times a second, we do it on the airplane. And what you're seeing here is a typical controller that is used in airplanes. You would stabilize it. You can stabilize the airplane with this if it's not stable enough. You can actually destabilize it too if you would like to. You can design this in different forms where you can navigate now with your airplane. You can design a whole autopilot with this idea. Of course, the architecture looks a lot more complex. We will talk about this in this semester. But the idea is always the same. You measure things, send back, multiply with something, go back and alter the control of the airplane so that the airplane behaves differently. Now this is always a little interesting because the pilot will sit here, give an input, and say, oh, the airplane is flying so nicely. Look at this. I'm giving a pilot input, nice pitch up. I'm doing this, nice roll. In fact, we are working here behind in the back, and it doesn't even know. I remove this, connect R directly to this thing. The airplane might not be flying as nice. It might be unstable. It might be very rocky. Okay? Or let's say there's a lot of turbulence, there's a lot of wind, and the airplane just does this. Everybody in the airplane will get sick, right? But if you design this thing right, then there might be a wind, there might be turbulence. The pilot might not be a very good pilot either. But the airplane will fly nicely and the way you want it to fly. Now, what are we doing as engineers? And what are you going to do as aerospace engineers? What is your job? Your job is to design this thing. Okay? Your job is to design this thing. And the design of this will be different from airplane to airplane. Okay? So let's say you want to design a fighter airplane, right? You want to do a lot of fast maneuvers. You want to have an agile airplane. What happens at that point is you want to make this whole airplane fly rather fast, right? So the design here will be quite different. Let's say you have a passenger airplane and you don't want that. You want quite the opposite. You want to have a calm, straight flight, no matter what the turbulence situation looks like. If there's a wind or gust, you want to fly as nicely as possible, so that meals are getting served nicely, and you might get something nice to drink, and you have stewardesses going in and out, right? If you do a good job over here, everyone will be happy in the airplane. Okay. Let me give you another perspective of this. Let's say you designed an airplane where the aerodynamics is not very nicely done. What does it mean? It's not very stable. It is from small winds and gusts, it's moving a lot. Well, who's gonna make that airplane, bring that airplane in a better shape so that you find more customers? Well, it's you, the controls guys. If they do a good job over here, okay, then the airplane will fly nicely. It will maneuver nicely, although the aerodynamics inherently wasn't very good, which means if you go from here to here, that thing, the aircraft itself, was not very good. But if you design it nicely, it will be fine. Okay? Now, here would be a question, of course. Is this K matrix here a constant matrix? The answer is, most of the time, no. We need to change it during flights in different flight regimes. If you're flying fast, it will be different. If you're flying slow, it will be different. If you're flying high, low altitude, high altitude, right? This cable might change. So we call this gain scheduling. This is typically the gain, okay? We call it the gain. And in this case, it would be the gain matrix. Here it would be just the controller gain, and here would be a gain matrix. Okay, we'll talk about this more later. All right? So it might change from flight condition to flight condition. So where is this all coming from? Where is this all coming from? There's one more point to this whole story, and it's this part. X dot equals AX plus BU. This is a linear system. Everyone understands that this is a linear system? This is not a nonlinear system. A nonlinear system would look like this, right? A function that's x and u, and a function can be very nonlinear. This is a linear system. So again, if you have taken flight mechanics with me, you will remember how we obtained the linear system. This is kind of a continuation now. We obtained the linear system in flight mechanics. We started with nonlinear equations. We chose a trim point, remember, which was an equilibrium point. And then we linearized everything around that equilibrium point and obtained this linear matrix, this linear system. And this linear system was only valid in a closed neighborhood of the trim position, of the equilibrium position, right? Remember that? Okay. So, when I say the airplane is represented by a linear system, what would be the first question you ask me? It would be, which linear system are you talking about? Around which equilibrium point was this linearized? Right? This is only valid around an equilibrium point of the airplane. Not everywhere, around one equilibrium point. So, therefore, when I use this in my controller design, I'm really designing a controller for only one equilibrium point, for one trim point. Let's say 30,000 feet, I don't know, 800 kilometers per hour, standard atmosphere, passenger airplane, whatever. For that flight condition, you can calculate this linear system, right? You can calculate this, you can calculate that. You can calculate the A and B matrices. Remember how you calculate the A and B matrices? Don't remember, again, I go back to flight mechanics. We linearize things. How do you linearize it? We use small perturbations, remember? And this is all valid for one equilibrium point. So we do everything around an equilibrium point here. Okay? Isn't that how you define sort of stability? We also talked about stability in flight mechanics. Stability is a property of an airplane or of the equilibrium points. What? Equilibrium points, of course, right? Stability is the property of the equilibrium point. An equilibrium point can be stable, unstable, right? And an airplane will have a lot of equilibrium points. A flight at 800 kilometers per hour is an equilibrium point. Maybe a flight at 600 kilometers per hour is another equilibrium point, right? So all these equilibrium points, there are many, there are infinitely many, in fact, equilibrium points, might have all different stability characteristics. For example, helicopters are quite different. When you are at low velocities, at low speeds, the equilibrium points at low speeds for a helicopter are mostly unstable. But as you go faster and faster, after 40, 50, 60 knots, the helicopter starts having equilibrium points that are rather stable. So, if you design a controller at 70 knots for a helicopter and in hover, those controllers will look quite different. The K matrix will look quite different. At hover, the helicopter is unstable. 70, 80 knots, fast forward flight, you are becoming stable. So obviously the controller will do a lot of work in hover and probably less work at 70, 80, 90 knots. So therefore the controller will look very different. The architecture probably looks very similar though. This architecture, the idea, the methods, they will all look very similar. What's going to really change is this one. Okay? Any questions? Is this all clear? Does this make sense? Oftentimes what I hear from students who take controls, they say, well, we have been in the controls class for one semester, but we still don't know how to apply this and what it is good for. We have drawn a lot of boxes, we have found numbers, and we don't know what this all means. I don't want to start this course like that. Do you understand what we will be trying to do? It is really this. Okay? I will call things U, X, Y, whatever, it's a lot of symbols, but reality is really here. You have control surfaces that move around so that the airplane does something. If you have a gust coming from one side, the airplane needs to do that, right? How does it do it? Well, it changes the direction of the ailerons, right? Gives a little bit of an aileron input and moves to the other side. So it would be here. So that would be the control input U. And then what does the airplane do? Well, we all feel it in our bodies. We can see it, right? The inner ear works fine and tries to understand what's going on. But the computer can only understand what the airplane is doing by looking at the sensors. Sensors, right? Without the sensors, the computer won't know what the airplane is doing. So you get all that information, do some calculations, and intervene with the pilot input. The pilot is here, we intervene with it, and we change whatever happens here. And this is what we call a controller in the broad sense. If you look at airplane terminology, you would hear something called stability augmentation system. It's called a SAS. Airplanes, helicopters, all this, they have a SAS. It's called a stability augmentation system, which means augmentation means, improve it, make it better. Improve the stability of the system. So improving the stability of the system looks just like this. You take the state, multiply it, intervene with this, with the pilot input. You intervene over here. We call it the stability augmentation system. So it just stabilizes the airplane, makes it fly nicer. Okay. Overall, how the airplane flies has another name. Did you remember that? I talked about this in flight mechanics. It's called handling qualities. How does the airplane handle? Is it nice to fly? Is it nice to fly? Is that an airplane that does whatever it does and it's not listening to my commands? Right? Those questions. How does it handle? Handling qualities. Handling qualities. We improve the handling qualities of airplanes using controllers. Using just that. So the pilot will give a pitch up. Maybe the airplane doesn't want to pitch up. So this computer here says, oh, that's not enough. Let's give a more input over here so the airplane goes really up. But the pilot doesn't even know. He just did this, and the elevator is doing a lot of work to give you that pitch up. So that would be increasing the handling qualities. Okay. Another thing you can do, as I said, is you can do navigation with this. You can adjust your velocity. Okay, adjust your velocity. If you want to go fast, you want to go slow. If you're a helicopter, you can adjust your height, even with an aircraft too. So we call this, all these things, like where you do navigation, where you have some modes, let's say velocity modes and altitude modes. In a broad sense, we call this autopilots. Okay. In reality, name them whatever you do. These are the functions of these things. These are all controllers. They all work similar to this, if not equal. Okay. Of course, there are lots of tricks in this. If there were not tricks, if this was simple, then we wouldn't be sitting in the class, and you probably wouldn't be having a job after you graduate. Because if it's very simple, then nobody's going to pay you, right? Anyone can do it. Why would they pay you to do that if everybody can do it, right? The reason they will pay you is because it will be difficult. So you in some sense, you need to be happy that it's difficult. Because it's difficult, not everybody can understand it, right? And hopefully you will, and therefore people will pay you. That's what a job is, right? So there are lots of tricks you can do here, and hopefully we will learn about the essential things in this class. How you trick these things to make it a perfect, or at least a useful controller. Any questions? Okay, so one thing. A linear full state feedback controller uses a lot of matrices. A, B, C, D. We will not be using much the D, but A, B, K matrix. So we will be doing a lot of matrix algebra. Okay? And that's why I want to talk a little bit about matrices and linear algebra in the next few hours. This is a review. I will go rather fast. Okay, rather fast. And if you feel like you don't know enough, please review it at the beginning of this course now, before it's too late. Because this, here you had a lot of transfer functions, remember? It's all transfer functions. Here, it's all matrices. So you need to know linear algebra. Okay? Any questions? All right, let's give a short break and I'll go back to the review.